I'm Rain Pakerin, and welcome to the CU Boulder MCEN 1024 Did You Know Chemistry Project final video. Polylactic acid, or lactic acid, or polylactide, most commonly called PLA, is something that has struck me as quite significant in my life. It has always been my ambition to be proficient in various skills that would help me be a great engineer, but 3D printing was among the first skills that was easy to get into and develop. From a very preliminary starting level to a level of understanding and operation, correlated with how material processes and manufacturing settings influence the performance of the extruded thermoplastic polyester into desired additive manufactured products. Elaborating further, PLA is a plastic used in 3D printing with a melting temperature in the range of 150 to 160 degrees C, commonly sold on rolls of filament in a diameter of 1.75 millimeters or 2.85 millimeters, weighing 0.5, 1, or 2 kilograms total. The design of this is such that the filament can be fed using two small gears from the roll of filament into a hot end, where filament is heated up to a specific temperature. For PLA, commonly in the range of 180 degrees C through to 220 degrees C, and extruded at a specific flow rate with the assistance of a slicer application, which takes 3D models and, using user input, converts the 3D model into a step-by-step instruction manual for a printer on how to create an object by incrementally extruding filament in a mountain of locations, eventually creating the object. This milestone focuses on the key chemistry and material science relating to the topic chosen. I intend to discuss the chemical method by which PLA can be made from simple biologically derived products, and additionally I aim to discuss why small changes in the temperature settings when PLA is printed, or slight amounts/moles of additive added, for example color dyes, strength and ductility enhancing additives, drastically influence the resultant print, and why the basic structure of PLA is so desirable as a simple yet modular material for the prototyping process with 3D printing. The basic structure of PLA is a repeating modular chain with the backbone formula of C3H4O2, meaning there's a repeating pattern in a long molecular chain of a specified form and composition of 3 carbon atoms, 4 hydrogen atoms, and 2 oxygen atoms. Graphically, it can be difficult to accurately represent an entire molecule of PLA because of the quantity of these chain links of C3H4O2 that compose one molecule of PLA. The molecular weight of PLA is roughly 128 to 150 U kDa, or kilodaltons, where 1 dalton is roughly equivalent to an atomic mass unit AMU, meaning each molecule is 128,000 to 152,000 atomic mass units. Given each chain link in the polyester has an atomic mass of 72.063 atomic mass units, each molecule of PLA is composed of a chain of roughly 1,776 to 2,109 chains of C3H4O2. In the image shown, this quantity of chains would be the N value beneath the expression. In the process of researching this topic, I was curious why plastics are composed of long chains and why that's useful to the application of plastics as materials. First of all, I discovered that polymers are formed through a process called polymerization, where monomer molecules of similar or identical structure bond together into larger structures, in the case of PLA, comically long chains. Polymerization can either be in the form of addition or condensation. In the scenario of additional polymerization, monomers are required to have a carbon-carbon double bond and undergo an exothermic addition reaction. PLA does not have a double bond from carbon to carbon, but PLA does form from the condensation polymerization method, which is characterized by an exothermic water-producing reaction. So, the reason why plastics are in long chains is because the polymerization method takes place in monomers, creating the very high molecular weight chains. Furthermore, these chains can entangle with each other in a spaghetti-like form, entangling being connected to the intermolecular forces between these polymer chains rather than an actual chemical interaction, as is visible in the graphic below, causing the material to have a form of additional strength. The greater the length of the molecular chain, the higher the molecular weight, and intuitively, the easier it is for the polymer chains to become entangled with each other, resulting in strong mechanical properties. As a quick elaboration, the van der Waals, hydrogen bonding present in the PLA polymer, and dipole interactions encourage these chains to tangle together. Note that because of the inherent variation in the process behind PLA's creation, the chemical reaction which produces PLA for monomers, not all chains are of the exact same length. This results in variation in the quality of the filament, thinking back to 3D printing from length to length, or from the manufacturing standpoint, also batch to batch. From an engineering standpoint, it is important to understand the resultant material properties derived from chemistry and material science in order to determine engineering application. Below this paragraph is a true stress-strain curve of PLA informing the discussion on the desirability of PLA as the material of choice for 3D printing and prototyping. From the graph, it's visible that the linear deformation region can extend all the way to 60 to 70 megapascals, meaning that the stress can be achieved without permanent deformation to an object composed of PLA. While the 3D printing process introduces new potential for structural failure of a printed object beyond that which a solid PLA object would have, vacancies between layer lines, etc., with tuning to the settings involved with fabrication of a PLA printed object, these weaknesses can be minimized and a 3D printed object can approach the strength of an injected molded object of identical shape. The main chemistry-related topic of discussion for this project is how one might go about creating PLA from a biological material. A helpful article by the Polymer Innovation blog has given me the basics of how the chemical process behind this works. PLA is composed of carbon, hydrogen, and oxygen, abundant in plants. More specifically, kernels of corn are primarily composed by mass of starch, which is a polymer composed of D-glucose monomers with monomer formula C6H12O6. Note that chemically, C6H12O6 contains the same amount of carbon, hydrogen, and oxygen atoms as 2 times C3H4O2 plus H2O. That is to say, it is apparent how chemically the glucose from corn could undergo some kind of chemical reaction such that the breakdown of the polymer chains of glucose produces the monomer of PLA, with water as an additional byproduct. Step 1 in the process to convert this D-glucose derived from corn to PLA is to extract the D-glucose alone from corn. This is a physical process as opposed to a chemical process. Wet milling is used to mechanically separate starch from the corn kernel with water. This is accomplished by wetting cleaning corn kernels, then running the wet kernels through several layers of grinding and milling, removing various components of the corn procedurally. For example, the germ, the fiber, the protein, and then finally the starch. Once the starch is extracted from the corn kernel, step 2 is to use enzymes or acids to extract the dextrose, or D-glucose, from the starch. As one method of many, the copolymer ergonet 155 can be used in this extraction step. Step 3 in this process is to obtain lactic acid from the D-glucose. Multiple complex steps involving various enzymes accomplish this task as visible in the graphic. Chemically, it's most relevant to note that this fermentation process involving the biological element of ATP, familiar as an active ingredient in metabolic processes of glucose, is achievable quite easily with commercially available enzymes. The production of lactic acid from glucose was historically done as early as the 19th century, hinting at the ease of production of PLA. Alactite has the structure visible in the graphic below and chemical formula C3H6O3. Once lactic acid is obtained, the final step is a series of heating steps under various conditions in tandem with the introduction of a tin catalyst, chemically only removing H2O from the lactic acid and going through various reforming steps of the existing mass of the reactant, e.g. the polymerization discussed earlier, which finally results in the polymer chain of PLA. A useful additional topic is how additives to PLA as a basic plastic material can enhance and specialize the application of PLA filament. For example, Polymaker's Polymax PLA, with modified additives to enhance impact strength as opposed to basic PLA filament, accomplishes this goal with flying colors, as is visible in the first graphic below of an experimental test by the YouTube channel CNC Kitchen. While the exact chemicals involved with the impact strength improvement as a result of introducing an additive to the PLA is not public information, an educated guess would say that the introduction of a copolymer is involved with this material property improvement. The principle is that in the polymerization process, rather than only having one chemical monomer compose an entire plastic polymer chain, 2 alternating monomers can be intermittently bonded together in an alternating fashion. This mixes and hybridizes the material properties from the two monomers' lone properties, were they polymer chains, into one plastic with the best of both components. The temperature at which a 3D printed object is created at extrusion temperature of a nozzle for a set material, for example PLA, greatly influences the strength of the print for mechanical reasons. The melting temperature of PLA in the 150 to 160 degrees C range means that the higher the print temperature is, the more of an opportunity the PLA has to melt onto itself and bond layer by layer into a strong 3D printed object. In contrast, choosing a printing temperature that is lower can result in incomplete melting, which makes the object weaker. I'd like to thank my professor and TA for making it possible to finish this project, and for everyone who's given me advice on it along the way. The following are my references, and I would highly suggest looking in the links below for interesting YouTube videos and the URLs to websites that helped me along this research path. Have an awesome day.